In this lecture, we will discuss about different fundamental operations of image processing and an overview of image processing. So, let us understand first how images are represented in computer. Let us consider an image which is displayed on your screen and consider a small portion of the image as it is shown by this rectangle. If I zoom this portion, then you will find the enlarged portions of the image, and you can see that some of the details are more visible here, and there are certain kind of rectangular regions of the pixels or regions which are also visible. And if I further zoom this area, then you will observe that further zooming those areas, there are small squares of uniform illumination. Those values are shown here by the numbers in those square. So, finally, as you can see that in the image at the very bottom level of representation, every point has a number, and that number is representing the brightness value at that particular point. However, while displaying it on a screen, it is a small area which is representing that point, and this brightness value is also shown at that point. So, the image is represented as a 2D array of integers. So, these numbers are all those integers, and in a 2-dimensional array, as you know, you require to also mention the array size. So, those array size will be the width and height of the image. For example, in this case, for this image, the width is 256, which means there are 256 points along its width, and height is 384. There are 384 points along its height. When we consider representing a colored image, there would be 3 such 2-dimensional arrays, each for representing one of the primary colors like red, green and blue. If you consider any particular point of this array, all the respective locations, all the respective array elements, corresponding array elements with the same array indices, they will represent a combination of color by these 3 primary colors. So, you will have a red component of the color, if I can display only with the red color in the screen, and a green component of the image which is displayed here by the green color, and the blue component of the image which is displayed by blue color. Now, once we superimpose all these colors on a screen, then you can get the color representation of the image itself. So, an image in this case is represented by 3 2-dimensional array, and when this information is stored in a computer hard disk in the secondary storage, you know that any information in the secondary storage is stored as a file. Similarly, image has to be stored as a file, and a file, it consists of a stream of bytes. So, in this case, every byte or a collection of byte will represent a pixels, and we can consider that is as a stream of pixels. However, to represent the image in your program, in your computation, you require other associated informations of the images of that image, and which has to be stored also with this stream. Usually, they are stored ahead of the stream in a very predefined format, and which is called header of the image file. For example, a header can consist of this kind of informations, like it should contain the width information, height, the number of components, which means in this case for a color channel it should be 3 for a colored image, number of bytes per pixel. As I mentioned that a pixel could be represented by a number of bytes. In a very elementary representations, usually it is 1 byte per pixel, and where the values unsigned integer values vary from 0 to 255 per pixel. Of course, there should be an end of file representation for a file, and there are different standard file formats which are available for an image representation. they are very much standardized and documents are available. So, when you get an image file in these formats, you should know the corresponding format and you should parse the header and get the images. So, these are some example formats like TIFF, BMP, GIF, etc. So, let us consider how an image is formed in an optical camera. Let us consider in a camera which is represented here, a lens of the camera which plays a very critical role, and there is a plane where the image points are projected, where the points of the three-dimensional scene, they are projected on a two-dimensional plane, and that is actually the focal plane usually of this particular lens, and where the images are formed, and those points are finally sensed by corresponding sensors and they are digitized and you get a digital representation. So, if I consider that how a point in a three-dimensional space is mapped to an image point, so let us see how it can take place. If you consider a point P where a light is reflected and that light is passing through the center of the lens and intersecting at the plane of projections or the image plane. So, this point which is represented here by small p is the image of the same point which is represented here by this capital P. So, image has been, in this case image formation has taken place due to the phenomena of reflection as you can see. So, there is another information which is also encoded at this image point, that is the amount of reflection, that amount of energy that is received at this point which is reflected from the point P. So, that is the action of lens which takes care of this particular property, tries to get as much as energy, reflected energy, tries to put them together on this plane P, collects it and focused it on this point P, and that is what is called also focusing, and that is why you get a very sharp picture if it is properly focused, a sharp point representation of the same point. So, this is another encoding. So, the amount of energy which is reflected from this point, that should be received here and that is sensed. So, the interpretation of this image is that it gives a brightness distribution in this two-dimensional plane, where at each point you get the corresponding, it is proportional to the amount of energy reflected from its corresponding scene point. Let us look at minutely that once again what is the rule of projection that I mentioned here, and that provides you a very simple mathematical tool to compute, given a point P in the three-dimensional world, what should be its corresponding image point in a two-dimensional plane. So, as you can see in this case, that this can be formed if I draw a line from this point through a particular fixed point O, which is here the center of the lens, and extend that ray which hits the corresponding image plane, and that intersection point defines the image point of the three-dimensional scene point. So, this is the center of projection as I mentioned, and this is the image plane, and we can summarize this rule as image points formed by intersection of the ray from a point P and passing through this center of projection O with the image plane. This kind of projection is known as perspective projection. But this is not the only way images are formed. There could be other kinds of imaging principles, other rules of projections can take place. For example, in this case what I am going to show here, the image formed image of this cube where one of the planes of the cubes have been projected here, and as you can see all these points are parallelly projected to this plane. There is a particular direction which has to be considered in this case for this projection. It could be normal to the plane, it could be any other directions in a three-dimensional plane. So, this rule we can summarize in this way, that image points formed by intersection of parallel rays with the image plane. And this kind of, one example of this kind of imaging is X-ray imaging, where X-ray beams, parallel X-ray beams, it passes through our body, through bones, through tissues, and then it intersects the corresponding X-ray plate which acts like a image plane in this case and forms the image, and this projection is known as parallel projections. Let us take another imaging principle. Let us consider you have a surface of an object, and your imaging sensor, there is a transmitter which transmits transmits a electromagnetic wave or some acoustic wave, and then the reflected wave is received by a receiver. So, the duration, the time interval between transmission and reception, that can be measured, and if you know the velocity of the wave, you can compute the corresponding distance from this point. And consider you scan radially, you are taking this at every regular interval and you are scanning it radially over the surface points, and you can get, or you can consider also you can translate this transmitter receiver along certain directions and performs this action repeatedly. So, for every surface point in that path, you will get a distance. So, you can measure the distance. Not only that, the amount of reflection what you get from the surface, that would also determine the orientation and surface property of this particular material. So, one example is this echocardiograms, where acoustic waves are used and ultrasound waves are used, and so this is one kind of example. So, if I summarize that what is an image, how do I define an image? It's in a very short sentence we can say it's an impression of the physical world, and just to make it a little more, just to elaborate it, we can say that it's a spatial distribution of a measurable quantity encoding the geometry and material properties of objects. So, now I will be discussing a few concepts and operations which are there in the image processing, and in this course we would require some of these concepts. As I mentioned earlier that you do not require to go through the first level image processing course to attend this particular computer vision course. These are the primers that I will be discussing here. However, it would be better if you follow some image processing textbooks and know more details about these concepts. So, let us consider the first a very simple concept of images, a very first level statistics of the distribution of these pixel values, and which can be captured in the form of a frequency distribution of the brightness values in this particular image. Here I have shown an image of a scanned page. We can say these classes of images are document images. Once again, in this image also you have those brightness values at every pixel, and as you can see there are two types of pixels are there mostly. One is the text, it depicts the text of the document, the other one belongs to background. Usually in the histogram you should have found you should have obtained a bimodal kind of characteristics, but in this case since you get so many white pixels, so it is more skewed, and particularly the distribution in the text zone, it looks little flat. So, we will come to this point how this could be processed further to make it more bimodal, but presently let us consider this is let us concentrate on this fact that an image histogram is nothing but the frequency distribution of this brightness value, and from this frequency distribution you can get the probability distribution, you can convert it into a probability distribution of the brightness value. If I normalize the histogram, that means all these frequencies should be divided by the total number of pixels of the image, then you get the probability distribution of the brightness values. So, one of the problem of document image analysis is to separate the foreground from background, and this process is called binarization process. So, one of the simple technique of binarization is using a threshold value to declare that whether a pixel is foreground or whether it is background. So, in our present context, the example what I have given here, foreground is the dark pixels and background is the bright pixels, which are white region of the document. and pixels after binarization, it could be set to one of the two values. For example, we can consider 255 represents the white region and 0 represents the text portions or dark pixels. Say this is what we can consider. One of the simple algorithms of this binarization could be as follows. Say you can choose a threshold value t, that is one of the brightness value in that intervals, some value in the brightness interval, and a pixel greater than t is set to 255, otherwise it is set to 0. So, this is a very simple algorithm, and let us see what is the effect of this algorithm. Say you consider that this document, and this is displaying the particular histogram. Let us consider a particular value, say 156, where you perform this thresholding, and then you get an image like this. So, you see that there are only two types of pixels, pixels with the value 0 and pixels with value 255 in this case, when your threshold value is 156. If I choose another value, say 192, you get also another kind of binarized image, and you can see the difference between these two images. So, if the threshold value is higher, then you get more foreground pixels, your text becomes sharper here, but then there are more spurious noise in your document also, which is not desirable. So, what is the optimum threshold value? What is the desirable threshold value which will make my text sharper, which will look the foreground also sharper, or detect the proper foreground pixels, and also it should not contain it should remove the noisy part of the pixels also. So, this kind of manual choice of thresholding may not help when you are trying to process various documents, and one of the objective would be that to automate this operation of this thresholding. So, one of the techniques that I would be discussing here is the Bayesian classification of foreground and background pixels of a particular image. In this case, we consider that our histogram of the image is a bimodal histogram. A schematic diagram is shown here. It is, so there are two modes, there are two peaks in this histogram, and our assumption is that most of the pixels which are around this mode, around its particular peak, those pixels are coming from the foreground pixels, and the pixels which are coming from the background, they are centered around this particular mode. So, we consider there are two classes of pixels, and these are the symbols of this class, these are the notations of this class in this case. Say let us consider W1 and W2 just for the abstract representation of this problem. So, what we need to do in this case, we need to compute the probability of a class W1 given x and probability of a class W2 given x. So, this is because in a Bayesian classification rule, we assign the pixel x to class W1 if the probability of W1 given x is greater than probability of class W2 given x. Otherwise, we assign it to W2. That is a Bayes classification rule. So, how we can compute this this particular probability, which is called incidentally posterior probability in this case. So, we can apply Bayes theorem there, and in the Bayes theorem you can see that in this case I have described the theorem. So, consider this pixel x. So, probability of a class given that pixel x can be computed from these three quantities. So, this is probability of the class itself, then probability of x given this class and divided by the probability of x. So, this is the Bayes theorem, and it is simpler to compute, particularly this quantity is easier to compute than this quantity directly, because this is called likelihood, and we can assume that the pixels which are around this part, they form a distributions which are coming, a class distribution which are coming from the foreground pixels, and we can assume they are Gaussian distribution. Similarly, the pixels, so this is the probability distribution of the pixel x given that they are coming from class W1. And similarly, for the background class also, we can consider another probability distributions for the background class, and that would be the probability distribution of x given W2. So, these probabilities are called likelihood. That could be computed easily rather than computing this directly. And also, you can compute probability of omega itself, class probabilities. If I assume that some threshold value is chosen, then these proportional areas can give me those two probabilities. I will describe it in the subsequent slide. But what is interesting to note, that actually you may not use this probability of x at all in these computations, because after computing these two, you need to compare only these values. That would, because this is proportional to these values, given a particular x, Px is already given by the data itself. So, let us see how these computations can be carried out, and there is a algorithm by which we determine these thresholds. We call these algorithms as expectation maximization algorithm. So, let me explain this algorithm here. So, let us consider that histogram once again, histogram of the image or probability distribution of the pixels, and let us assume a threshold value initially, say at this point. So, this value divides the intervals, this brightness interval into two halves. So, one we can consider this half belongs to say foreground region, and this half belongs to the background region. And so, this is a representation for the foreground part, and say this is a representation of background part. So, what we can do given this threshold, we can compute probability of W1 and probability of W2 by computing the area of this part and also areas of this part, and take the proportional areas of each region to compute that values. So, this is how the probability of class probabilities could be computed once given a threshold value. And then after that we can concentrate only these values, these classes only, and from there we can compute the parameters of say probability of x given W1 by assuming it Gaussian, and similarly we can also compute parameters of probability of x given W2 by assuming it Gaussian. So, if I relook at the Gaussian distributions function, it is a Gaussian distribution function, as you can see. There are two parameters, one is mu, which is the mean of the distribution, another was is sigma, which is the standard deviation of this distribution. So, what you need to do in this case to compute the probability, this likelihood probability, you just simply you need to compute these parameters, then you can compute the probability of any value x given those parameters. So, let us assume that we call the parameters, corresponding parameters for the class W1 as mu1 and sigma1, and corresponding parameters of W2 as mu2 and sigma2. So, next what we will do, that we will be considering the and this is how the corresponding parameters are computed in this case. You can see probability of W1 is computed as the area of Px from, it is a summation from 0 to threshold. Probability of W2 is just its 1 minus Pw1, because it is a complementary part of the area, and then this is a mean from this region, and this is a standard deviation from this region, and similarly mu2 is the mean from this region, and sigma 2 square, there is a variance, or sigma 2 is the standard deviation which is from this region, and this is how we are computing. So, we are computing the variances with of these values and mean of these values, and these are all simple mathematical arithmetic expressions of weighted means and weighted variances. So, if you look at the statistics, book of statistics, it would be very clear how these values are computed, why these expressions are there. So, once we get these values, then we are determining a new threshold value such that the probability of W1 by x is greater than probability of W2x. So, as soon as it becomes less, then we choose that threshold value, choose that threshold value, and that value would be a new value. So, we expected this should be a threshold value, but after computing this parameter, after maximizing the probabilities of occurrences of these pixels, then we found there is a better threshold value which will be giving you a better probabilistic occurrences of these observations. So, we iterate this process. So, that would be my new threshold value, and we will be iterating this process till the process is converged. So, this is what is your Bayesian classification based binarization method. And there is another method also we can consider here, which is almost similar and which also defines an optimization function by which you can get the threshold value. So, this optimization function is the between class variance of the particular two classes. So, between class variances are also, as you can see, it is defined by those parameters which I have discussed earlier. So, this is the class probability of W1, this is the class probability of W2, and these are the means of each classes. So, given a threshold value, I can compute this sigma square B, like probability of W1 from this part, probability of W2 from this part, then mu1 can be computed from here and mu2 can be computed from here. So, you consider that you are computing this value at every pixel value from in your interval, say 0 to 255 for example, and you consider that pixel value where the between class variance is maximum, and that you consider as your threshold value. So, this thresholding principle, this thresholding technique is proposed by Otsru, and it is known as Otsru thresholding technique. So, the example of this particular processing, you can see that with that particular document image, we have computed these Otsru thresholds, and which is 157 in this case, and it gives this kind of image. And if I consider the Bayesian thresholds, then we find another image. Incidentally, though the threshold values are same, you can see that there is little bit of difference between these two images, though quality of these two images are almost similar. This difference happens because we would like to make this histogram bimodal. So, before applying Bayesian classification, we processed the image so that the histogram has a sharper modes also in the foreground zone. So, how we are processing it, I will discuss in the next part. So, in this case, so this is what is the method which I was referring at. It is a contrast enhancement method, and here the concept of pixel mapping is used. The pixel mapping concept is that you have an input pixel and which will be mapped to an output pixel in such a way that dynamic range of the input would be expanded. That means, suppose in this case dynamic range is from 0 to this value, which could be say half of the interval approximately, but in the output we are converting that dynamic range from 0 to 255. That makes the pixels sharper, contrast sharper. And one of the property, of course, that you need to mention, that you need to preserve, that this function has to be monotonically increasing, because if you have two pixels x2 and x1 and x1 is higher than x2, then corresponding y1 also should be higher than y2. So, that keeps the consistency of displaying brighter pixel brighter and darker pixel darker. So, that is why you require this property. One of the popular function which is used in particular in this case is this function from the probability distribution of the pixel itself. So, this is a cumulative distribution, and you are scaling it by 255, assuming the range would be from 0 to 255. So, if I do this operation, we can see that we get a contrast stretched image where the features are more visible in this, are more prominent here. You can also look at this histogram. This histogram has a similar shape, but the dynamic range has been expanded, modes are more clearly visible. In fact, this is the technique what I was referring at. This is the technique we applied in the document which has been processed for binarization. So, with this let me stop here. This is the first part of this particular talk. we will go for the next part in the next lecture. Thank you very much for your listening.